In this video, we're going to look at a diagonalization example that involves the rational roots theorem. So the rational roots theorem is something that you may have seen back in high school algebra class. If you don't remember it or haven't seen it before, that's okay. I'll review what it says. So here's the example. Let's let A be this 3 by 3 matrix, and we want to diagonalize A if possible. And recall that what that means is we want to find matrices P and D, where D is diagonal and P is invertible, such that A equals P times D times P inverse. Okay, so if I want to begin to try to diagonalize a matrix, we need to first find the eigenvalues. So to do that, I need to look at the determinant of A minus lambda I. So let me put some vertical lines to indicate I'm going to take a determinant. And the diagonal entries of A each are going to get subtracted by lambda. So we'd have negative lambda, we'd have 1 minus lambda, and then we'd have 2 minus, let me give myself more room, 2 minus lambda for the diagonal entries. The other entries stay the same as 1, 1, 2, 2, 3, and 3. So now let's take the determinant. So when we do a cofactor expansion to compute this determinant, there's no great row or column that's going to simplify the computation tremendously. I don't have zeros in this matrix when I'm taking this determinant. So at this point, I just kind of have to dive into it. What I'm going to do is let's just expand along the first row. I don't have to do the first row. I could do others or other columns, but let's just do this. So I would take my first entry, negative lambda, and then remember, technically the sign of this first entry is considered to be a positive. So we have a plus in front of this entry. And then times the determinant where I cross out that row and I cross out that column of the matrix that's left over. So that's 1 minus lambda, 2, 3, and then 2 minus lambda. Okay, so let me just erase those extra lines that no, not that one, that one. Okay, that I drew in so I can see my matrix one more time. Okay, and then we go to the next entry, which is this 1. And the sign for that starts to alternate, so I'd put a minus in front of it, times its corresponding determinant. So after I cross out that row and that column, what I'd be left with is we'd have 2, 2, 3, and 2 minus lambda. And then I go to the next entry, which is a 1 in that row, and I alternate the sign again. So instead of a minus, I'll do a plus, times this corresponding determinant. So I cross out the row this is in and the column this one is in. And what I'm left with is the smaller 2 by 2 matrix. So the entries 2, 1 minus lambda, 3, and 3. Okay, so now let's simplify. Okay, so what we have is we have this negative lambda in the front. Negative lambda times, and for this 2 by 2 determinant, let's first multiply 1 minus lambda times 2 minus lambda. And that'll give us lambda squared minus 3 lambda plus 2. And then I have to subtract what I get when I multiply the 2 and the 3 together. So minus 6. Okay, and then after that I'll have minus, and then I could just write minus bracket. So the 1, I'm just going to sort of absorb that into this negative sign. And then if I multiply the 2 and the 2 minus lambda together, we get 4 minus 2 lambda. And then 2 times 3 multiplied together, that's 6. So I subtract the 6. And then I'll have plus. So the 2 times the 3 is 6. Minus. And then 3 times 1 minus lambda, that's going to be 3 minus 3 lambda. We'll close that bracket. Okay, so let's continue to simplify. Okay, so we have negative. Actually, let me go ahead and distribute this negative lambda in. But before I do that, let's just note that 2 minus 6, well, I know what that is. That's negative 4. So if we distribute in the negative lambda, we're going to get negative lambda cubed plus 3 lambda plus, 3 lambda squared, and then plus 4 lambda. Within the next bracket, the 4 and this negative 6 combine to make negative 2. So now if we distribute this negative in, I'll get plus 2 lambda, and we'll get plus 2. And then within this next bracket, this would simplify to 3 plus 3 lambda. And then I have this plus in front of that whole thing. So that'll just stay as plus 3 lambda. So now if we combine like terms, we have the negative lambda cubed. So we have 3 lambda squared. That's the only lambda squared term, 3 lambda squared. For the lambda terms, there's a 4 lambda, 2 lambda, 3 lambda. That gives me a 9 lambda. And for the constant term, there's 2 plus 3, which is 5. Okay, so we have this whole thing. This is our characteristic polynomial. This is P of lambda. That's usually our notation for the characteristic polynomial. So what makes this harder to factor is the fact that it's not just a quadratic. It has a higher degree. It's a cubic. It has degree 3. And one of the ways that we can factor this is by using what's called a rational roots theorem. So the rational roots theorem gives us a systematic way to sort of guess what the rational roots of this polynomial would look like. So if there's something that's going to make this polynomial equal 0, and that something is a fraction, it tells us what that fraction needs to look like. So here's the statement. So if P of lambda, our polynomial, has a rational root, so if it is going to have a rational root, so let's just call that lambda. So a rational number, recall that a rational number is a fraction of integers. So it's a number that can be written as a fraction of integers. That's why I've written lambda in the form a over b, where a and b are integers. And technically I should say one more thing. There's one thing that b is not allowed to be equal to. It can't be equal to 0, because the denominator of a fraction cannot be 0. Okay, so then it turns out that a, this number on the numerator, needs to be a factor of. And I'm going to refer back to my example here. The a would have to be a factor of the term, the coefficient 5. So the 5 is the constant term. And b would need to be a factor of the leading coefficient. And technically the leading coefficient here is we have a negative 1 technically in front of the lambda cubed. So the b would have to be a factor of negative 1. So that is the leading coefficient more generally. The leading coefficient. So keep in mind these terms that I'm writing in green, because this is what the more general case would be. The 5 and the negative 1 are just specific to this example that I'm looking at. Okay, so if we forget which one of a and b correspond to the leading coefficient, which one refers to the constant term, we could always do a simple example to help us figure it out. So the example I usually think of is, if I look at lambda squared minus 4 equals 0, well, I know what the answer to this is. I know that lambda equals plus or minus 2, but let's write this as a fraction. This is plus or minus 2 over 1. So in this example, notice that the numerator, does it divide the constant term, the negative 4, or does it divide the leading coefficient, which is 1? Well, it divides the constant term. It divides the negative 4. And then the denominator, the 1, divides the leading coefficient. This divides the 1. There's technically a 1 in front of this lambda squared. So that's one way I could sort of remember, oh yeah, the a, the number on the top, divides the constant term. And the number on the bottom divides the leading coefficient. We could come up with a simple example like this and just remind ourselves. Okay, so let's list out what these possible rational roots could be. So if lambda, if the root of this equation is going to be a fraction, what is it going to look like? Okay, so I'm going to write my answers. I'm going to let my possibilities in fraction form. So on the numerator, I need to have a factor of 5. So let's start small. I know 1 is a factor of 5. But I also know that negative 1 is a factor of 5. Okay. And then for the denominator, there's going to be more, but let me just start with these. For the denominator, it's got to be a factor of negative 1. Okay, so there's two possibilities. The denominator could either be 1, or the denominator could be negative 1. So if I just put a 1 in both of those denominators, I get the first number ends up being 1, the second number ends up being -1. If I had instead put -1 in both of these denominators, we actually would have gotten the same two numbers, just in the opposite order. So it's fine if I just put 1 in both of these denominator spots. Okay, so now if I keep going, what are the other factors of 5? Well, I could have 5, and I could have -5. And then again, for the denominator, I'll put 1 and 1 for the factors of -1. And notice that I don't need to worry about putting -1 on the denominator here, because it'll still give me the same overall numbers. It'll give me one of them will be 5, one of them will be -5. So overall, we have 4 possibilities for what lambda could be. So at this point, we have to try them. So I usually like to go from small to big. So I'll try lambda equals 1 first. So let's plug that into our polynomial. Let me scroll up. Let's scroll up so we can see it a little bit. Let me zoom out. Yeah, so if we plug in lambda equals 1 into this polynomial, we'll get -1 cubed plus 3 times 1 squared plus 9 times 1 plus 5. Okay, so now let me zoom back in a little bit. Okay, and if we add these together, we'll get 16, and that is not equal to 0. It's not equal to 0, so this is not a root. So I'll put a sad face. That didn't work out. So that can happen sometimes when we do the rational roots theorem. So now I'll try another one. Let's try lambda equals -1 now. So maybe we'll get lucky with this. So if I plug that in, we'll get -1 cubed plus 3 times -1 squared plus 9 times -1 plus 5. And if we add these numbers together, we do get 0. So that's awesome. That means, so the fact that when we plugged in -1, it worked. That means that lambda equals -1 is a root. And that's awesome for our purposes. So at this point, it might be tempting to say, wait, can't I just now try 5 and -5, and maybe one of those will be the other root? So yeah, if we get lucky, that'll happen. But the issues with just doing that is, in the rational roots theorem, one of the possible issues is, this basically says that if our polynomial is going to have a rational root, then it's going to have this form. But it doesn't guarantee that our polynomial has a rational root at all. So it's totally possible that the other roots of this polynomial might be irrational, like things with square roots. And the rational roots theorem will not help me find roots like that. The other thing that the rational roots theorem wouldn't help me with is taking into account if something is a repeated root. Like, I don't necessarily know if -1 is a repeated root at this point. So what I'm going to do is I'm going to show you guys a technique that is more general for figuring out, well, what are the remaining roots? It turns out we need to use polynomial long division. Okay, so let's talk about long division. So long division. So this might have been something that you saw back in high school, in the algebra class, but if you don't remember, that's okay. I'll review how it works. So what we would do is we would take our characteristic polynomial, which was negative lambda cubed, plus 3 lambda squared, plus 9 lambda, plus 5, and we need to divide this by the thing that we know is now a factor. So the fact that -1 is a root means that lambda plus 1 is a factor, because plugging in -1 into this makes this factor become 0. That's why it's a plus 1. Okay, so what I do first is I need to multiply lambda plus 1 by something so that when I multiply that thing by lambda, I'll get the negative lambda cubed. So I need to multiply by negative lambda squared. So I like to put the negative lambda squared above the similar degree term below it. Let me space this out a little bit more. So long division. But if we wanted to write the negative lambda squared above the negative lambda cubed, there's nothing wrong with that. I just personally like to write the matching degree terms above each other. Okay, so now I multiply the negative lambda squared times the lambda plus 1. So when I do that, I'll get negative lambda cubed. And again, here I definitely need to match up the like degree terms. And then multiplying it by the 1, I'll get negative lambda squared. And just like we use with regular regular long division with numbers. Now we subtract. So make sure I put a parentheses around this so I don't forget to distribute my negative. So I take this black line here, so the original polynomial, and I subtract this blue line. So when I do that, what I'll get is the negative lambda cubes will cancel, and then I'll get 3 lambda squared plus lambda squared, because I'll get a double negative. And then I carry these terms at the end down. So 9 lambda plus 5. And the reason I'm carrying them down is technically I'm subtracting, I'm doing this, all this black, these black terms minus these blue terms. So the 9 lambda and the 5 are part of that. And now I repeat the process. And I gotta ask myself, well, what do I multiply lambda by to get 4 lambda squared? And that's 4 lambda, positive 4 lambda. So notice I've written it above the lambda term down here. So when I multiply 4 lambda by lambda plus 1, we'll get 4 lambda squared plus 4 lambda, and now we subtract. So make sure that I put a parentheses around this. And subtracting, we're going to get 5 lambda plus 5. So I do this one more time. What do I multiply lambda by to get 5 lambda, this leading term? I would multiply by positive 5. And if I multiply 5 by lambda plus 1, we get 5 lambda plus 5. So now I subtract again. And when I subtract this time, we get 0. And when we get 0, that means the lambda plus 1 divided evenly into our polynomial. So we need this remainder to be 0 for this division to work, to go in evenly. So at this point, we can factor our polynomial. So we now know that negative lambda cubed plus 3 lambda squared plus 9 lambda plus 5, when we factor it, this equals lambda plus 1 times this term at the top, this quadratic, the negative lambda squared plus 4 lambda plus 5. Okay, so now what's left to do is factor this quadratic, and that's not too bad. Okay, so I've carried this over to the next section of the page where I have a little bit more room to write. Yeah, now let's factor the quadratic. So we have lambda plus 1 in front, and factoring the quadratic, this isn't too bad. Factoring it, we get negative lambda plus 5 times lambda plus 1. So at this point, by setting this equal to 0, I find my eigenvalues. So lambda equals negative 1 or 5. And notice the multiplicities of these guys. The negative 1 occurred twice, so the algebraic multiplicity is 2, but for the 5, that only occurred once. So the algebraic multiplicity for 5 is 1. Okay, so next let's find, notice all I've done so far is find the eigenvalues. I haven't found the eigenvectors. So that's what's next. Find the eigenvectors. Find the eigenvectors. Okay, so I'm going to go through this for one of the eigenvalues. And for the other eigenvalue, I'll just show you what the final answer is. Okay, but it's going to be the same overarching idea. All right, so let's do this for lambda equals negative 1. Let's find the eigenvalues, the eigenvectors. So I look at a minus lambda I minus negative 1I. In other words, this is going to be a plus I. So if we add I to our original matrix, we'll end up getting, so A was 0, 1, 1, 2, 1, 2, 3, 3, 2. That was the original matrix A. And if I add I to this, so I is 1, 1, 1 on the diagonal, and then zeros everywhere else, what we'll get is we'll get the matrix 1, 1, 1, 2, 2, 2, 3, 3, 3. So that's kind of nice. So now what we need to do is we need to find the null space of this. So we have to find the null space of A minus lambda I to get the corresponding, to get the eigenspace, and then that'll let me find the eigenvectors. Okay, so we need the rows at this point to get our eigenvectors. So let's do negative 2 times row 1 and add that to row 2, and insert into row 2. And we'll do negative 3 times row 1 and add that to row 3, and substitute into row 3. And these, so this will keep the first row the same, 1, 1, 1. but it'll zero out the other rows. Okay, and now this is in reduced form, so I can write down the equation. So I just need to do it for the first row. And if I write down the equation, and let me just go ahead and isolate x1 already, I'll get x1 equals negative x2 minus x3, because I've already gone ahead and moved the x2 and the x3 to the right-hand side. So I kind of did two steps in one right there. Okay, so at this point, let's go ahead and write down what the solution x would look like, what our vector x would look like. So there's three entries, x1, x2, and x3. And this pivot variable, x1, is negative x2 minus x3. x2 and x3 are free, so we leave them how they are. So x2 and x3, leave them how they are. And then let's split this up into parametric vector form. This will be x2 times the vector negative 1, 1, 0, plus x3 times the vector negative 1, 0, 1. Okay. So at this point, if I wanted to form a basis of eigenvectors, I could just take this vector that I see here and this vector that I see here, and these would be my basis of eigenvectors for this eigenspace. So I'll call this one B1, I'll call this one B2. These are two linearly independent eigenvectors for this eigenvalue, lambda equals negative 1. Okay, so I mentioned before that I would show you the process for getting the eigenvector for one of the eigenvalues carefully, and we just done that. For the other eigenvalue, I've just gone ahead and done the steps. So at the end, for lambda equals 5, we ended up getting just one free variable. So our eigenvector here is 1/3, 2/3, and 1. So I've called this one B3. Sometimes it's useful when we get an eigenvector with fractions to notice that we can multiply an eigenvector by something that's not 0 and get another eigenvector. So I, for example, could multiply this by 3 and get the vector 1, 2, 3. And that looks a bit nicer because it doesn't have fractions. And this is a perfectly valid eigenvector that I could use that corresponds to lambda equals 5. Okay, so at this point, let's think about how many total eigenvectors we have. Well, we had two eigenvectors for lambda equals negative 1. And notice that that matched up with the multiplicity of negative 1. The multiplicity was 2. And the dimension of this eigenspace is 2, because there's two linearly independent vectors here. For lambda equals 5, there was one eigenvector, one linearly independent eigenvector. And that matches up with its algebraic multiplicity for lambda equals 5. Okay, so our eigenvectors, we have three linearly independent eigenvectors overall. We have three linearly independent eigenvectors total. And because our matrix was 3 by 3, it's going to be diagonalizable. Diagonalizable. Okay, so let's just write down what D is and write down what P is. So the matrix D has the eigenvalues as the diagonal entries. Okay, so negative 1 occurred twice, and then 5 occurred once in terms of their multiplicity. And it doesn't matter which order I write these in, as long as when I write their corresponding eigenvectors in the matrix P, I make sure that they correspond. So let's put zeros everywhere else here. So the eigenvectors for negative 1, we might have to scroll up a little bit for these guys. For negative 1, one of them was negative 1, 1, 0. The other one was, negative 1, 0, 1. And then for 5, for the eigenvalue 5, let's go ahead and use this form that didn't have the fractions. Let's use 1, 2, and 3. So usually in a diagonalization problem, we get to stop here. Once we write down what D is and what P is, we can go ahead and stop. So one question that we might have is, wait, if I've taken this third column here, in a sense, and I've changed it from the numbers that I was getting here, these fractions, wouldn't that change my diagonalization? And the answer is no, it wouldn't change it. Because if we think about what A is P times D times P inverse. By changing this third column of P, we change the third column of P here, but that also is going to affect P inverse. So by changing this column in P, it's going to change what P inverse looks like. And those two changes sort of counteract each other. So overall, it'll still be a legal diagonalization. So that's why it doesn't matter whether I choose this fractional form or whether I choose this form without the fractions.